In this video, we're going to continue talking about random variables and probability distributions. Now, there are two special distributions. The first being what we're going to talk about in this video, the two discrete distributions, which are binomial and geometric. And then in a future video, we'll be talking about one continuous distribution, which are our normal distributions. So let's go back to our binomial and geometric distributions, which are our two discrete distribution types. Now, suppose we decide to record the gender of the next 25 newborns at a particular hospital. What is the chance that at least 15 are female? What is the chance that between 10 and 15 are female? Out of the 25 newborns, how many can we expect to be female? These questions can be answered using a binomial distribution. Now, the properties of a binomial experiment are that there are a fixed number of trials, and we use an n to denote the fixed number of trials. Each trial results in one of two mutually exclusive outcomes, success or failure. Outcomes of different trials are independent. The probability that a trial results in success is the same for all trials. Now, the binomial random variable x is defined as x equals the number of successes observed when a binomial experiment is performed. Are these binomial distributions? Tossing a coin 10 times and count the number of heads. Yes. What about if you deal 10 cards from a shuffled deck and count the number of red cards? No, the probability does not remain constant. What about the number of tickets sold to children under 12 at a movie theater in a 1-hour period? No, it's not a fixed number. Now, the binomial probability formula is where we're going to let n equal the number of independent trials in a binomial experiment. P is going to equal our constant probability that any trial results in a success. So the probability of x is going to equal n factorial divided by x factorial times the quantity n minus x factorial times p raised to the x times the quantity 1 minus p raised to the n minus x, where from n to x, our combination is going to be n factorial divided by x factorial times n minus x factorial. Now, if you've got your book, Appendix Table 9 can be used to find binomial probabilities. Technology, such as calculators and statistical software, can also perform these calculations. So let's get back to our question in the hospital. Instead of recording the gender of the next 25 newborns at a particular hospital, let's record the gender of the next 5 newborns at this hospital. Is this a binomial experiment? Yes, if the births were not multiple births, like twins or triplets or things like that. So we're going to define the random variable of interest. So what should we let x equal? What do you think? Let x equal what? Yeah, let x equal the number of females born out of the next 5 births. What are the possible values of x? Well, you could have 0 babies, or 1, or 2, or 3, or 4, or 5 be females. Will a binomial random variable always include the value of 0? And what will the largest value of the binomial random value be? To answer these questions, remember that x is the number of females born out of the next 5 births. So in general, as we're thinking about this, 0 will always have a value there. It will always be included. And the largest value of the binomial random value will be the actual number of experiments or observations that you're monitoring or seeing. So here we want to know, what was the probability of success? Here, for each individual birth, we have a probability of success of 1/2, because the baby will either be a female or a male. Let's keep up with this example. So what is the probability that exactly 2 girls will be born out of the next 5 births? So we're wanting to know what's the probability that x equals 2. So here we're going to find the combination. We have 5 total births using a combination, and we're looking for 2. So we're going to take that formula for our combination and multiply that by 0.5 squared times 0.5 cubed, and that's going to give us a value of 0.3125. So what is the probability that that less than 2 girls will be born out of the next 5 births? So here we're looking for x is less than 2, so the probability of 0 plus the probability of 1. So we're going to add those together. So here we're going to have our probability for our combination out of the 5 births, 0, our female, times 0.5 to the 0 power, times 0.5 to the 5. So notice those add to 5, just like up here, 2 plus 3 was 5. Now we're going to add that with the probability of 1. So out of the 5 births, we want 1 female. So we're going to have our 0.5 to the 1 power. So this first exponent will always match this value right here. And then again, our exponents need to add to our 5 right here. And so because I'm already using the 1, that tells me this needs to be a 4. When I do that, I'm going to get a 0.1875. Now, let's construct the discrete probability distribution table for this binomial random variable. So here we have 0, 1, 2, 3, 4, 5. So we have the probability of 0, the probability of 1, probability of 2, probability of 3, probability of 4, and probability of 5 together, like all just shown for us. So we want to know, what is the mean number of girls born in the next 5 births? Now, because this is a discrete distribution, we could use mu sub x equals the sum of x times p. So we'll go ahead and multiply each of those together and then add them together to get a mu sub x of 2.5. Notice that this is the same as multiplying n times p. Formulas for mean and standard deviation of a binomial distribution are mu sub x equals n times p, and the standard deviation, or sigma, and sigma sub x equals the square root of n times p times the quantity 1 minus p. Let's go back to our newborns example. So how many girls would you expect in the next 5 births at a particular hospital? So our mu sub x is going to equal n times p, or 5 times 0.5, which equals 2.5. Now, what is the standard deviation of the number of girls born in the next 5 births? So here we're going to take our sigma sub x equals the square root of n times p times 1 minus p. So we're going to have the square root of 5 times 0.5 times 0.5, which is going to be 1.118. Now remember that in binomial distributions, trials should be independent. However, when we sample, we typically sample without replacement, which would mean that the trials are not independent. Now in this case, the number of successes observed would not be a binomial distribution, but rather a hypergeometric distribution. The calculation for probabilities in a hypergeometric distribution are given more tedious than the binomial formula. Or they're even more tedious than the binomial formula. But when the sample size n is small and the population size capital N is large, probabilities calculated using binomial distributions and hypergeometric distributions are very close. When sampling without replacement, if n is at most 5% of capital N, then the binomial distribution gives a good approximation to the probability distribution of x. Let's go back to our newborns again. Now suppose we were not interested in the number of females born out of the next 5 births, but which births would result in the first female being born. How is this question different from a binomial distribution? That's right, we're going to keep going until we get to the first female being born. So which birth would result in that? So here are the properties of a geometric distribution. There are 2 mutually exclusive outcomes that result in a success or failure, and each trial is independent of the others. The probability of success is the same for all trials. So a geometric random variable x is defined as x equals the number of trials until the first success is observed, including the success. So what are the possible values of x? Well, we could have 1, 2, 3, 4. So how far will this go? Well, it'll go to infinity. So the probability formula for the geometric distribution is we're going to let p equal the constant probability that any trial results in a success. So our probability of x is going to equal the quantity 1 minus p raised to the x minus 1 times p, where x equals 1, 2, 3, and so on. So let's look at an example here. Now, suppose that 40% of the students who drive to campus at your school or university carry jumper cables. So your car has a dead battery and you don't have jumper cables. So you decide to stop students as they are headed to the parking lot and ask them whether they have a pair of jumper cables. So what are we going to define as our random variable here? Well, we're going to let x be the number of students stopped before finding one with a pair of jumper cables. Is this a geometric distribution? Yes, because we're going to go until we find somebody that has jumper cables. So we're going to let p equal 0.4. So what is the probability that the third student stopped will be the first student to have jumper cables? So we're looking for what is the probability that x equals 3. So we're going to take our 0.6 quantity squared times 0.4, which equals 0.144. So what is the probability that at most 3 students are stopped before finding one with the jumper cables? So here we're looking for the probability that x is less than or equal to 3. So we're going to take the probability of 1 plus the probability of 2 plus the probability of 3. So we're going to have 0.6 raised to the 0 power times 0.4 plus 0.6 raised to the 1 power times 0.4 plus 0.6 squared times 0.4. And that's going to equal 0.784. So notice here, again, because it's supposed to be our n minus 1, we're asking 3 people, but our exponent will be a 2. It'll always be 1 less than what we're looking for.